I would like to run through a couple of freefall example problems. First one. Maybe I'm going to start with something pretty straightforward. I'm standing on the ground and I'm going to kick a ball straight up from the ground at 30 meters per second. I would like to know, how high does the ball go? First, I'm going to start with my table. First, I'm going to start by setting a couple of things. I'm going to say upward can be my positive y direction. So I'm looking at a coordinate system where y is just up. I'm also going to set my origin so that the ground will be y equals 0. Effectively, what I'm saying is that my x-axis is right here parallel to the ground, or at the ground, but I'm not going to throw x into this because I'm just dealing with still a flavor of one-dimensional motion. How high does the ball go? I'm going to make my table. Y initial, Y final, V initial, V final, acceleration, time. I'm starting on the ground, so I'm starting with y equals 0. I'm looking for y final. That's the thing I'm really hoping to find. Y initial, or V initial, that's 30 meters per second. And it is positive because I'm going up. V final. When I get to the top of my motion, I will have a V final of 0. Let me show you what I mean by that. If this is at the top of the motion, so a ball is going up, and then the ball is going to be coming down afterwards. A moment before I reach the top of my motion, I am still moving up, and my V is still a positive number. If my V is still positive at the top, that means I'm still moving upward, and a moment later I would be higher. That's not the top yet then. A moment after I've reached the top, and I'm on my way down, my V will be a negative number. If at the top my V were already negative, that means that if I back up time by an instant or two, I would be higher up, which means I'm not at the top anymore. So at the top of my motion, I have to have a V final of 0. Acceleration. As soon as this ball is in the air, so I kick this thing, and as soon as it leaves my foot, as soon as it's in the air, the only thing acting on it's gravity. Gravity is going to accelerate this thing at 10 meters per second squared in the downward direction, so we get a minus sign. The time, I don't know how long it's going to take to get to the top. Now I'm going to write my same kinematic equations that I've written plenty of times. I'm just going to rewrite them for y instead of x. The first equation, if you remember, does not have v final in it. The second equation does not have x, but in this case y, in it. And the third equation doesn't have time in it. Okay, I am looking for y final. If I'm looking for y final, I know equation 2 is not going to be helpful to me because y isn't in there. I can't solve for something that's not there. So I'm looking at equation 1 or equation 3. Now I have information about v final. I know my v final is 0. What I don't know is the time. I can plug into this bottom equation because it doesn't require me to know the time. So I'm going to do that. I'm going to say 3. V final squared is V initial squared plus 2a delta y. My V final is going to be 0. I'm looking for delta y. So I can solve. I'm going to get delta y equals negative V initial squared over 2a. If you do not jump straight from this first step to the second, that's okay. Take a minute, pause the video, work through how to get from here to here. Now I'm going to plug in my numbers. Negative 30 meters per second squared over 2 times negative 10 meters per second squared. And that works out to be 900 over 2 is 450 over 10 is 45, and the negatives cancel. I'm going to get 45 meters for my change in y. Being that I started from the ground, that means that is my final height. One more example. Maybe I would like to know if I stand on top of a building and I'm actually going to use a little bit of information from this last problem. So I'm still holding onto a rope so I don't fall. I'm going to take a ball and I'm going to drop it now. I'm going to say that we start off 45 meters up. There's the piece of information I'm borrowing from before. We're going to just drop it, and I would like to know, how long does it take to hit the ground? Okay, I'm looking for how long, so I would like to find time. How long does it take to hit the ground? It tells me that my y final is going to be 0, assuming I am still working with this kind of an axis where I say upward is my positive y-axis and the ground counts as my y equals 0. I'm going to set up my table and plug in what I've got. My y initial, that's going to be 45 meters. I'm starting 45 meters up, and my y final is 0. My v initial, if I am dropping this, then I'm starting from rest, so my v initial is going to be 0. I'm going to skip v final for a second. This is a free fall situation. My gravitational acceleration is going to be negative 10 meters per second squared, and the time, I don't know, but it is what I'm solving for. I want to slow down 1 second. V final. V final, I don't know what it is. It is a really tempting and common thing to say V final 0. I'm going to hit the ground, of course it's going to come to a stop. And I agree with you, once you hit the ground you are going to come to a stop. The problem is, this is a free fall problem. Free fall works when the object is not in contact with anything and is just being pulled by gravity. If I were to kind of map what's going on with this ball, as soon as it leaves my hand, it's in free fall all the way down until just before we hit the ground. Once we hit the ground, now the ground is going to exert a force. We haven't talked about forces just yet, so don't worry too much about that, but understand the ground is going to exert a force on the ball. The ground changes the physics of the problem. It's no longer in free fall, so we can't use this same situation anymore. So anytime that we are doing this kind of a problem, or really projectile motion problems, which we'll be doing soon, anything like that, we are looking, the problem starts the instant after you have let go, so it's no longer in contact with your hand or anything, and it ends the instant before you hit the ground. Once you've hit the ground, once you're interacting with the ground, this doesn't work anymore. So we're looking for how long does it take to almost hit the ground. I'm going to write my same equations again. Equation 1. Here we go. I'm looking for time. If I'm looking for time, equation 3 doesn't have time, so that's not going to be particularly helpful. Equation 2 does have time in it, but it also has v final in it, and I don't know v final. Equation 1 is going to be the way to go. So equation 1 says y final is y initial plus v initial time plus half a t squared. I can put this in at 0 And now I've got an equation that I can solve. I also have an initial velocity of 0. So what I get, 0 equals y initial plus half a t squared. It looked like it was going to go quadratic, but it doesn't have to. I'm going to get t by itself, so t equals negative 2 y initial all over a under square root. Again, if you're not completely following that quickly, take a second, pause it, and work this out in between. I'm just solving this equation for t equals. And then I'm going to plug in the values. Negative 2 times 45, that's negative 90, divided by negative 10 is positive 9, and the square root of that is 3. It's going to take 3 seconds to hit the ground. Now I do want to do one more thing, because it's a helpful piece, I think, is let me find v final. What this would look like as a problem is find the impact speed. The impact speed is just the speed that you are moving right before you hit the ground, the wall, whatever it is that you're hitting. So we're going to find the impact speed, which means find v final. Now I have the time, so I can use equation 2 without any trouble. Equation 2 says v final is going to be v initial plus a t. My v initial is 0. So just acceleration times time. V final is going to be negative 30 meters per second. My impact speed, because speed is the scalar, it's the magnitude of my velocity vector, my impact speed is going to be 30 meters per second. My impact velocity would be negative 30 meters per second in the y direction. If I go all the way back here to this problem that I had left behind, giving this an initial kick of 30 meters per second from the ground, got the ball to go 45 meters up. If I take the ball from 45 meters up and drop it, it's going to be going at 30 meters per second when I get to the ground. What that means is that this is a time symmetric case, and free fall will be. If I'm standing at the ground and I kick this ball straight upward at 30 meters per second, it's going to travel up, come to a stop at the top, because that's what the top is, and then travel back down. When it is about to hit the ground again, it's going to also be moving at 30 meters per second. At this point, we are not moving at all. The entire way, I have this gravitational acceleration. I've got negative g when the ball is here. When the ball is higher up and moving slowly, I've got negative g. When the ball is at the top and has stopped completely, gravity does not care. It's going to keep pulling down. When I'm halfway back down, gravity is still the only acceleration. And when I am about to hit the ground but haven't hit it yet, I still get negative g. That acceleration vector is constant the entire way. My velocity vector on the way up starts out big and upward. Acceleration points in the opposite direction, so the whole time I'm traveling upward, my velocity vector starts out big, gets smaller, comes to a stop, gets bigger, bigger. My acceleration vector is constant. this whole thing, if I play this recording in the forward direction or in reverse, if I could play it backwards, I would get exactly the same result. And that is an important conclusion to be able to draw from freefall.